Dear colleagues, can you hear me?
Yes.
Okay.
Yes.
I'm very glad to welcome everyone in our session. I am the chairman. My name is Alena Zamышляева, and I'm glad to announce our first speaker, who is Dingqun Deng. I'm sorry if I mispronounce your name and surname. He's from Beijing Institute of Mathematical Sciences and Applications from China. And the topic of his talk is on the screen. You're welcome. You have 25 minutes.
Thank you. Today I will talk about the global resistance of non-cutoff Boltzmann equation. This equation is to describe the dilute gas. So let's start. First, I will give an introduction to Boltzmann equation, and then corresponding to this Boltzmann equation, we will define a semigroup and we give the time decay analysis of this semigroup, and then we can use this time decay to find out the global resistance of the Boltzmann equation. Okay, so we start. Firstly, we give the definition of the Boltzmann equation. It will look in this way: Ft plus V dot gradient xf equal to QFF. Here, QFF is a bilinear collision operator defined in the following way. And the left-hand side of this equation is actually a transport equation. So the right-hand side is the collision term, and it will be defined in here B times F prime G prime star minus F G star. Here, the prime and star represents the velocity variable. What does it mean by V star and V star prime, V prime? It means that the V and V star are the velocities of two gas particles before the collision, and the V prime star are the velocities after the collision. So, in the elastic collision, they will satisfy the conservation laws of momentum and energy. So in a simple way, it will represent it in like here. Actually, if we have two particles looks in this way coming from this side and the other particle coming from the other side, and which has velocity V and V star, then very simple physics will tell us they will go out with velocity V prime and V prime star. So you can see in this graph that there's a meaning of the velocity variable in this equation. All right, so next we may give an introduction of this B function. The B function will be defined by a relative velocity to the power of gamma times another function B of cosine theta. Cosine theta, here theta is the angle between V minus V star and some direction sigma. So without law of generality, we can assume that V minus V star times sigma is larger or equal to 0. And moreover, we will assume this B cosine theta to be approximately to the power of theta to the power of minus d plus 1 minus 2s. Here s is between 0 and 1. D is the dimension of the space. So this will be the basic definition of this equation. And next, we may give a linearization of this equation. We are looking for the solution F near the equilibrium, which is actually the Gaussian distribution. We will call it the Maxwellian. This is actually the Gaussian distribution. So we will do a linearization by letting F equal to this Gaussian function plus the Gaussian to the power of 1/2 times small f. Then the original Boltzmann equation will be transformed into this way. Here, the left-hand side is also a transport equation, and LF is the linearized Boltzmann operator, and the last part is a bilinear term, which will be very small because F is near the equilibrium. So that means F will be a small function, well, which means it will be small in some norms. So here F times F will be even smaller. So this will be a smaller term. And the main part we will analyze today will be this linearized Boltzmann operator, which we call it, which will be presented in the following way. All right. So I will introduce some classic results in these films. In 2011, Grassman and Schrein gave a famous result on the existence theory of the non-cutoff Boltzmann equation in GEMS and the Advance of Mathematics. And another group give another proof by in gamma and JFA, and this is for the existence theory. And for the regularity theory in the same group, and there's another group called Chen and He, published in AMA in 2011. But in any cases, they didn't use the semi-group method, which is work for another version of Boltzmann equation. This is for the non-cutoff Boltzmann equation. There's another version for Boltzmann equation, which is called the cutoff. So for the cutoff case, there is a semi-group method, but for the non-cutoff case, there's not yet. So in this talk, I will talk about how to use the semi-group method for non-cutoff Boltzmann equation. So firstly, we may use some symbolic calculus definition. So we may see let gamma to be this will be the Euclidean metric, and we call a symbol A belongs to this Sm gamma if this derivative is smaller than some function m, and we'll call it the well quantization, which is actually defined in the following way. The AWUX is defined by, it looks like the Fourier transform in the variable x plus y over 2, and take the Fourier inverse transform on the variable psi. Okay, so this is called the well quantization. In some case, we will call the pseudo differential operator. All right, so this is some tools. And next, it comes to semi-group, we will use some very basic theorems from the strongly continuous semi-group. We will call the operator A is dissipative, and only if for any x in the domain of D, in the domain of A, there is this some element Jx such that the real part of Ax pair with Jx is smaller than 0. So for a dissipative operator on a reflective finite space, such that lambda I minus A is surjective for some lambda, then the closure of the A is densely defined and generates a contraction semigroup. So next, we will use this theorem to generate a contraction semigroup for Boltzmann operator. Here, we will define the decomposition for the linearized Boltzmann operator. If you remember it, it's called L. We will split it into two parts. One part is A. Well, you may not really see the definition. This is some technical argument. We will call the A will be the positive part, as you may see in the following theorem, that the real part of AFF is larger than, actually it is larger than 0. So here A, small a is defined here. this is actually some technical construction. So we may see the negative A will satisfy the definition of dissipative. So here the negative A part will generate a contraction semigroup. Okay, so for the part K, we can prove that K, well, you see here is some P times V gamma plus 2S and times P. This P is actually some projection. So in this way, the K is, we can prove it is compact and maps L2 function to Schwartz function. So by using the bounded perturbation, we can prove that L generates strongly continuous semigroup, right? Because A generates a contraction semigroup and K is bounded, so L generates a strongly continuous semigroup. Okay, so next we will define the Fourier transform of this A, B, B, because there's a transport operator, if you remember it in the equation. So we define this Fourier transform of this part will be 2 pi I y dot v. Y is the variable after Fourier transform of x. So A will be the part for just negative A without the K. So in this way, we can actually give some spectrum structure of this operator B hat. Well, we can prove that for any y0 large, for any y is sufficiently small, there is some sigma such that on the right-hand side, sorry, maybe we just see this -1. On the right-hand side of this negative nu1 is some constant. There will be only some eigenvalues, which will be called the point spectrum. There's actually d plus 2 eigenvalues. And these eigenvalues has the asymptotic expansion such that the first order is pure imaginary, and the second order is negative. So this will be used in the time decay for the semigroup. Okay, you remember it? That the first order is pure imaginary, and the second order is negative for this eigenvalue. Okay, so next, we can prove that the semigroup generated by B will have the following time asymptotic behavior. That it will, the first part will be decayed in exponential decay, and the second part is binomial decay. Well, you may neglect the norm of this because it will be a little bit complicated to explain. But the main idea is that this semigroup generated by B will be decayed in binomial decay in time. Okay, next we give a sketch of this proof. Well, we first analyze the Fourier transform of B. So we start with the Fourier transform of B operator. We may use a famous formula in, well, we'll call it the inverse formula for semigroup, that the limit is taken in L2. Here, sigma 2 is some positive number, and we are going to use the Cauchy theorem for holomorphic function, because the integram of this in this integral is actually analytic. with respect to lambda. So we will use Cauchy's theorem in this graph. You may see we transform the integration on along the line on the right hand side to the outer part of this rectangle. So the result will be here, and you will integral from negative sigma y plus in to sigma 2in. You will anyway together it will forms this rectangle in this integral line. But if you remember that there are some eigenvalues inside near the y equal to 0. So near this 0, there's eigenvalues. We represent it in this e to the eigenvalues times pjf. Here pjf is the projection corresponding to the j eigenvalues defined in this way, which gamma means the smooth boundary of the eigenvalues containing only these eigenvalues and separate from the eigenvalues, and it forms in this projection. Okay, and then in this way we can estimate the first we can estimate this projection, because when we take the absolute value, well, you can see the lambda j, the first order is pure imaginary, so it's actually 1. The second order is negative. So we may see the second order is negative. So actually the second order will be represented in this way. And then the first part of this integram we will do it in this way. That we use another function, smoothing function, to approximate this phi. Here phi is the lambda I minus b hat inverse acting on f. And the smoothing part will be tends to 0. And we are only need to calculate the phi epsilon convolution with phi. So here capital phi convolution with phi we're using the definition of this phi, and we rewrite it, put this inverse of lambda I minus b hat to the left hand side, and we can represent it in this way with some calculation. Then substituting this inside this phi, we can get with some suitable calculation, we can get the answers. So this is the main idea. Okay, we use another convolution with it, and we can calculate this estimate. Okay, and after getting the result on this is from negative sigma y minus in to negative sigma y to plus in. So we can have, using the Fourier transform, back to the semigroup for B. In the above, we actually calculate the estimate on semigroup generated by B hat, which is the Fourier transform of B. And using the Fourier transform and inverse Fourier transform, we can return to the estimate for semigroup on B. So with this Fourier inverse transform, which is integral on dy, we can have with some weight. There's some weight here where we can neglect that. And the main part is the time decay for this. So the second part is the time decay from eigenvalues. And the first part is from the e to the negative 2 sigma yt comes from here. comes from here. Is the integral is from negative sigma y. Okay, and then we can have the time decay for this semigroup. Okay, with this time decay, you can see that there's some singularity when t is near 0 because this t goes 1 over t2k goes to infinite. So we should do it in another way to get the local in time behavior, which is by using the local existence for this linearized equation. We will do, because B is some, remember that it is dissipative. And so if we do the inner product with F itself, we have the following. This is a positive part, and integrated for on time, then we'll get the initial data plus some bounded part for in B. So there's a time here, T0. So if we choose this time very small, that is bounded. It can be absorbed by the left-hand side. So this is bounded by the initial data. Okay, but okay, there's here the weight is A1 over 2. So actually we should use the zero semigroup to transform it into, transform this weight to the left, to the right-hand side to make it become A to the negative 1 over 2 by using the zero semigroup, and the details are neglected, okay? So with this local in time and large behavior of this semigroup, we can obtain the global resistance to the Boltzmann equation here with some initial data, such that only if the initial data is small enough in some norm. So here we define such norms. This is, I think, is very useful because this norm contains the semigroup on B. If we define such norms, the first part is actually some Sobolev space norm, and the second part we will first acting the semigroup on it, and then integrating on this tau on the E tau B. Then if we do the energy estimate, then when doing the time derivative on this, we'll get this part is become E to the tau B times BF. So by using the very basic property of semigroup, this is actually the derivative of tau on this E to the tau B. So this part will become the, here it will be the d tau on this E tau BF square. And after the integration, it will become a negative function. And if we put this negative function to the left-hand side of this equation, well, it will become a very good term because it's positive on the left-hand side. And there are some bad terms from B, which is this one is bad because it's positive on the right-hand side. If we want to absorb it, so we can choose this delta in this norm to be very small, and this C delta is smaller than the 1 over 2, then we will be absorbed by this part. So this become a good term. So which means that we can obtain a positive term from this norm. If you like to use it, this is very useful, I think. So with this, by another proof estimate on this gamma term, we'll get the priori energy estimate on this function. And you can see here the left-hand side is positive and the right-hand side is trilinear term is one norm times the norm square is trilinear, is triple. It's triple term, so it's good. And this gives the global existence. Okay, so maybe my talk just stop here, and thank you for your attention.